Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff, the great stuff, the very good stuff. This is the AAS Journal Author Series, and I am super happy to have Aidan Berres with us today. Hi, Aidan.
Hey, thanks for having me.
Sure. It is October 26, 2022 as we record this, and fall has arrived in Phoenix. We're actually a little cool this morning. And where are you located at, Aidan?
I'm located in Urbana, Illinois, at the University of Illinois, in my office.
Yeah, that's a student office, so we may get some noise going around, so that's all perfectly good. So fall must be in full swing in Urbana. At least all the corn stalks in the area must have come down or turned brown at this point.
Oh yeah, it's getting pretty big here, and there's leaves all over the ground, and all the trees are just looking very beautiful.
Nice.
My walk to the offices are very colorful.
Very cool. Very nice. And what is your current position there in Illinois?
My current position is a graduate student. So I'm a first-year graduate student in the astronomy department.
Very cool. Very good. That's great. And Aidan, so far in your one-year trajectory as a grad student, what do you like to do for research?
Well, since I'm a first year, it's always hopeful what I would like to do.
Sure.
Right now, I'm really hoping for, survey astronomy, something with Rubin, something with time domain sources as well. I'm moving away more from asteroid time domain stuff to more supernovae and looking at difference images through that.
Cool.
So I'm focusing on like extragalactic, supernovae, and time domains sources.
Very cool. Very nice. And that is going to bring us to this very lovely research note. Research notes of the AAS. Orbit, a validation package for orbit integrators. And Aidan, take us away.
Okay. So first off, I would like to thank the main PI for this project, Sarah Greenstreet, who kind of helped me move along with trying to get the other integrators supported for this package. Also with Joachim and Mario, they were very helpful. Joachim especially with helping me get through all the software challenges, trying to write everything, because there's just so many different input and output file formats and things like that.
Yes.
And then Edward Liu and everyone from B612 helping me get through this, which was they're very integral in helping me start the project and helping me get through it. Since this was co-sponsored by B612 and an LSSD grant.
Okay. Got it. Very cool. Good shout out. Okay, away we go. Orbit.
So Orbit is necessary, and it was called upon by lots of researchers that want to use open source integrators for tracking and identifying asteroids in observational data.
Okay.
And so with the advent of like LSST finding so many asteroids and having different asteroid determination softwares packages, recently B612 got their Precovery service out, which looks for asteroids through old data, and they need these types of open source integrators to try to determine those orbits. And so what my PI found and B612 found is that there isn't a real tester, an internal tester for these open source software, to the point where you don't really have something that can test, how accurate they fit orbits to themselves, and it's not very internal.
Right.
You may be able to test them to each other, but there was no real test or internal consistency. Right. And so what we did is we made our own testing framework and things like our own end-to-end test to test these the main three open source integrators. And so our testing framework begins with having the integrator generate ephemerides, so generating fake simulated observations, and then taking those observations, then fitting them to a new orbit using the same software.
Okay.
And that's used orbit determination. And so we have it at some kind of final orbit state.
Right.
And so now we can then take that initial orbit that we input and we can propagate that to the same final state,
I'm with you.
basically.
Uh-huh.
So what happens there is then you can difference them and try to, subtract the values, the orbit state values from each other to find the difference. And so if the integrator is internally consistent, we
Right.
should see that there is no difference. It should be zero. But
right.
yeah, we found that these integrators, with certain parameters that we can change, find that they're not fully internally consistent. They're very close. Some of them became very close, but some were not. But I'm not going to pick favorites here.
So I'm curious, is that I mean, I agree it's an internal consistency, is it? But you've also done an extrapolation from some point to the final point, right?
Yeah, and that's with the same software.
Yeah. Okay.
Yeah.
Good. I'm good. Super.
Yep. And so our supported integrators are the big three open source ones. So we have FindOrb, which was created by a amateur astronomer,
Cool.
Bill Gray, to study asteroid orbits using his own open source software that's freely available. And then we have OpenOrb, created by is it Helsinki or yeah, I forget fully where the OpenOrb's from, but yeah,
We'll find it.
OpenOrb was used heavily with especially with B612. They used it heavily with their pre-recovery service.
Granvik.
Yeah, Granvik.
Granvik.
Granvik. Yep.
Yep. Okay.
And so, yeah, with that, it used a little bit different. So it has it has the extrapolation fit, or it has the statistical ranging. That's what it was.
Right. It's
Yeah,
got a
so
little
that's a little bit different from the other ones in that it will try to fit it over short observations. Like if you only had 3 or 4 and it was over a really short time scale, it will try to fit that orbit as best as possible.
Okay.
And so we ran into some issues where with our tester, we tried to feed it too many and it started kind of breaking. And so we had to go back and try to split them up and try to figure that out. And so that was a real challenge. Trying to test with OpenOrb. And then we had OrbFit, which was a little bit more challenging to try to write a tester for, but it works, and it's
Cool.
it's also all Fortran based, so that was really interesting to try to parse through that.
Indeed.
But
Good.
yeah, so all these integrators are all open source. You can go and download them for free, and what's great about them is that you can run them locally, and you can look through its code and modify it as you will. And that's what we're trying to encourage here, is we're trying to find what for a given asteroid, what's like the best parameters to try to fit an orbit over. And so we have these internal consistencies to show like what method is good, or for a given asteroid type, like main belt, near Earth, trans-Neptunian object. What is the best parameters that you could use for it to be internally consistent?
Very good. Very nice.
And so with that, the object management system and also the wrapper, the Python wrapper for individual functions was also very integral. So with that, not only do we have a tester here, but we also have, in order to do to write the tester, we had to transport all these functions in Fortran and C++. We had to, wrap them into Python in order to get their functions all to work with Python, because this is all written in Python. And so what we have with that is we have these, all these integrator functions outside of the tester, basically. And so what a user can do is then use these orbit fitting softwares to, or use them outside of the tester in Python, basically. Right. So what you can do is you can input, a pandas CSV, and it'll output a pandas CSV with like ephemerides, your orbit determination fit, or your orbit propagation, your new state for orbit propagation. And so now a user can now use these with, minimal, Python knowledge. They don't have to know Fortran, and they don't have to know, random, input and output file types to use these now. And so I think that was another big part of this project.
Indeed.
And so, yeah, with the object management system, yeah, that was another thing, is like, we wanted to have an object where the tester could then use an asteroid through each different software, and it was all the same. And so the test is the same for each integrator, and we're not making compromises, special compromises for each one. So it's all the same test. And so that's what the object management system, we wanted something consistent.
Nice.
So we didn't want to call extra information for an integrator. We wanted all that information to stay in a specific Python object.
Very nice. Very good. Cool.
So some of our initial results. So debate over the style of the table or what columns should be in there was a big question for when we were creating this. And so we wanted to start off with the orbit state, which is a Cartesian state. So it's heliocentric coordinates from x, y, z, and then the velocity in x, velocity in y, and velocity in z. And so so that is our that was our orbit state that we begin with, and that's the orbit, that's the same formula that we end with.
Okay.
And so we wanted, so that was the big thing, was to show, what's the difference between our two final states, the one where we determine the orbit by generating the observations and then fitting, and then the state where we just propagated it, and we wanted to find the difference between those. And so that's the big difference. And so now we have other values in this table, including like the observatory code. Yeah. So we have things like the observatory code, the arc length. So we in the tester, you can then propagate over different times and different cadences. And so we have, like a month, a month's worth of observations every day. You can have, 70 days every 7 days, or you can have a year over about, 5 or 10 days. And so we tested over those three cadences when we were creating the software.
Cool. Very good.
And so, yeah, we have our epoch, and then we have our change in epoch, which is something which was another internal consistency thing. Like we hope that the time scales for each different state are the same. And so we should see that that number should be very small. And so this is with find orb, one of the integrators. And so we find that we can also input false astrometric error into our simulated ephemerides.
Sure.
And so we found that, with no astrometric error, it was fairly accurate. You see the delta R is very small, and and the delta R is very small, and then the delta velocity is also extremely small as well. And so that's a very good sign that this is very find orb is very internally consistent. We gave it no error. This is basically it running itself without any extra things. And so with the other errors, you could see that it does increase drastically. And that's what should be understood is, it can get kind of wavy after you add some simulated error.
Quite a bit, right?
Yeah. And so basically we can see that, if we do those delta states, we can then try to find, what could be causing this error, and what could be then causing this inconsistency. And that's where this is a helpful tool, in that if someone could use it and then identify what's wrong, they could go into the code or talk to the creator and say, okay, I'm finding this issue with this object, and I don't know if it's something that I'm doing, or it's something that's just inherent to the software, and if that could be fixed, or if that could be modified for my case.
Open source. Yep.
And then that's the great thing about open source, is that you can do that without running into any issues.
Right. Very cool. Very cool.
And then I guess an extra thing that I don't think I mentioned in the note was that for certain integrators, you can get out, I think for all of them, you can get out the initial input and output files that we use to test over, since my tester runs over, it creates and then outputs certain files, given the input parameters.
Okay.
And so what it does is that it saves, you can then specify a folder to then save all those files, so that if you want to go to, the creator of the software or someone else, you can say, here's what I input into the system. Here's what it output. What could be wrong with this? Things
Right.
like that, which, just increases the amount of, usability for this.
Yeah, it's like a minimal working example of something that isn't working. So, or not working as expected, let's put it that way.
Exactly.
Very cool. And so this is on GitHub, something like that?
Yep.
Very cool.
This is on GitHub. It also has a binder demo notebook. And so if you go onto the GitHub and you can click, I think it's like a start notebook or start instance, you can then start it and then try to, go through the demo with a binder server, which, can help, people get into the tutorial things and see how it actually works, which is I think one of the other goals of the project. So the launch interactive demo, that button. It may take a while though, but it should work.
Let's try.
Yeah, and also, I forgot to mention, it does have a documentation wiki
Very nice.
with the demo, just to explain like what's going on and how to use things.
I love the big note here.
Oh yeah,
Really active development. Yeah, software. Very cool. Very cool. Well, this is a well-needed tool. Aidan, I want to thank you so much for walking us through your very lovely research note. Congratulations on that.
Yeah, thank you.
Yeah, and since this is probably version, depending how one wants to count, version 1.0 or 0.0 or something like that. So let me ask, where do you think this goes over, let's say, the next 2 years or 4 years or whatever graduate student trajectory might be? Are there other integrators to put in? Are there additional test case asteroids, or just sort of where does this project go over the next couple of years?
Yeah. So since this is open source, basically, we encouraged people that are creating new Orbit integrators to then add theirs into our framework to see if they can use the tester for new integrators, which is something with the environments that I was using and the different classes, like different integrator class systems I was using in Python. It should be very easy to then write or to put in a new integrator into the tester. So that was one thing that we want to encourage new integrator software developers to then try to use our tester. Another thing would be to have people, with LSST or Rubin or people that are looking for asteroids to then use our tester to say, are our observations, and does this fit look good, or is it consistent?
Right.
So that was our main goal, is to have researchers use this to see what if this software is good enough or should be good for a fit,
right.
and to determine what parameters to use. And so that was the big thing. And so one of the ideas that was, I think, brought on by Mario was that we could talk to the developers of these integrators and say, maybe we could use our tester as like a GitHub action and say, if you change your code or push a new commit, it runs the tester and says, okay, you changed something. Okay, is it now more consistent or less consistent when you did that change? And maybe you'll give back some kind of data point or give back the table and saying, okay, this is a little bit more consistent for these jumble of asteroids. What could you do better? What has changed? Things like that. That would be another application of this that I think would be very helpful for the software development community for asteroid propagators.
Yep. Continuous integration.
Exactly.
Very nice. And the other nice thing about the package is, for a given set of observations, it seems like it's relatively easy to use multiple different orbit integrators, and then you can compare across the different orbit integrators. So in some sense, it's a nice framework of tying all of the open source ones together. So that's very cool.
Yeah. Yeah, you can, yeah, if you can, iterate over each integrator, and you can then put them all in a table and then see, okay, which one is more internally consistent with this asteroid compared to this one. And
Nice.
so that was another thing where we can then test which one is better rather than, what parameters
Verification,
are
so
better.
to speak.
Yeah.
Right. Right. Very cool. Nice. Nice. Well, I look forward to seeing Orbit progress over the next couple of years. It'll be very nice to see. So Aidan, thank you once again for walking us through your very lovely piece of software and your research note.
Great. Thank you so much for having me.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.